So I'm going to talk about a European project. It's a scientific project that is funded by the European Commission. It's within the seventh program for scientific research. It's called Success. It's a project in which new materials are developed that can be used in the electricity production. I'm going to talk about work package 7. It's on health, safety, and environmental impact. So Success stands for scale up of oxygen carriers for chemical looping combustion using environmentally sustainable materials. So I'm going to talk a bit about the different parts of the title. So what is chemical looping combustion? You see here there you see the air reactor. Yeah. Anyway, you see the air reactor there on the left and the fuel reactor on the right. So the air reactor, there is going air in and oxygen depleted air out. Because in the reactors are combined, they are interconnected, they are fluidized bed reactors. Fluidized bed means that you see the oxygen carriers there. Oxygen carriers are very small particles, and when you pour them, it's like they pour like a fluid. So that's why it's called fluidized bed. And the oxygen carriers are going very fast around. They are going from the air reactor to the fuel reactor and back. In the air reactor, they are oxidized, so they take the oxygen and they give the oxygen to the fuel, and so the fuel is burned. Oxygen carriers are made of metal oxides. They're complex metal oxides mixtures. And the great advantage of this way of burning gas is that the carbon dioxide can be captured, and it is a very clean carbon dioxide. There is no impurities in there, so it can be used for segregation or use. The scale up of the oxygen carrier. So in a previous program to this, there was a laboratory scale at a 300 watt production. Now the oxygen carriers are tested in the pilot plants, and it is the aim that it will be usable in future industrial plants for large-scale energy production. Why are it environmentally sustainable materials? Because they are oxides of manganese, titanium, calcium, magnesium, iron, aluminium, and copper. So they are substances of elements with a low concern for chronic health effects. There's also a work package in the project that looks at the recovery and the reuse of the oxygen carriers, so that there will be no or little waste. Then the environmental impact assessment. So we are looking at oxygen carriers during use in industrial setting, which is not there yet. We look at the impact on the workers, which I will talk about now today. And we also look at the impact on the environment, so via the wastewater, exhaust gas, and solid waste, but I will not talk about that aspect. So occupational safety assessment in a future industrial setting. How do you do that? Do a safety assessment for a situation that does not yet exist. So we look at process safety, and it's a kind of safety by design. First, we have to look at the worker's exposure during the use of the oxygen carrier at large scale. We don't have the large scale yet, but we look at exposure. Then we look at the health hazard, where we compare both. Then we have the risk characterization. So we compare the exposure concentrations with the safe concentrations, and then we know whether there is a risk. If there is a risk identified, then we will have to recommend safety measures. It can be for the equipment, it can be ventilation, and as a last resort, also personal protective equipment. As a follow-up, workers will have to be monitored for a number of elements, and of course the occupational air will have to be measured. Which oxygen carriers did we choose? We have first a manganese, calcium, magnesium, titanium complex oxide based oxygen carrier. It's made by a spray-dried material. And then we have two oxygen carriers that are impregnated on an aluminum oxide carrier. It's iron oxide and copper oxide. So three different materials, but they all look like very small spheres. Now, how do we simulate exposure during the chemical looping combustion? First, which route do we take? The inhalation route is the most relevant during this process. The aim is to estimate exposure during the handling of the intensely used metal oxide particles. And how do we do it? We have simulated a release of the oxygen of the carrier particles at the CLC workplace by generating dust and capturing the dust. Is it relevant? We think it is, because this situation is really a worst case situation, because quite some dust was generated, and it is a worst case scenario for the real world, so for the upscaled situation. Here you see how we generated the dust. So we have a vibrating feeder up there. There we pour the oxygen carriers in the hopper. Then it goes to the conveying jet there, to the stainless plate, and that is generating dust. When all the oxygen carriers up is in the plate, then again it is put in the hopper. And so it goes on for 1 day. This is the equipment to capture the dust. So we captured the PM100, so the particulate matter that is lower than 100 micrometers. Also the PM10, the particulate matter that is smaller than 10 micrometers. The online dust monitor is measuring the particle size distribution in real time. So in there above you see the hopper with the oxygen carrier. So the dust is captured. What do we do with the dust then? First of all, there is a characterization of these materials that are released to the workplace atmosphere, or to the simulated workplace atmosphere. For the particle size distribution for the PM, we collect PM100 and PM10. The PM100 is inhalable fraction, and the respirable fraction goes much deeper into the lungs. So it's it may cause more health effects. And then, of course, the particle chemical characterization was performed. It is a worst-case exposure assessment. We are going to compare these dust-generated elements with the occupational exposure limits. But with the dust, we will also assess the hazard of the released particles, because, as I said, with characterization, you need not only exposure, but also effects to see whether there are effects. But we will do the hazard assessment with in vitro tests, so no in vivo tests. You see the composition of the airborne dust concentration for the PM100 and the PM10 during the 8 hours measurements. The background, as you can see, PM100 and PM10 are quite alike. So about 25 micrograms per cubic meter. So most of the background is PM10. For the C28, it's the manganese, titanium, calcium oxide. Most of it is the PM100. So only about 8% is the PM10, so the smallest particles. For the iron impregnated aluminum oxide, 39% is PM10. For the copper impregnated 62% are the small particles. Just to have an idea, so the threshold limit value for total dust in Belgium for the PM100 is 10,000 micrograms per cubic meter, so we are far below that. And also for the PM10, it's 3,000 micrograms per cubic meter. It's also far below the TLV. We looked at the PM10, the particle size distribution, and for all three oxygen carriers, there were peaks at 2.4 and 6 micrometers. Here we see the concentration levels in the captured dust. So the background is very low. For the C28, only the copper, the aluminium, and the nickel could be measured. All the other concentrations are above the analytical upper limits. For the iron impregnated aluminum oxide, the iron and the aluminium are above the analytical upper limit, and the nickel is below the lower analytical limit. We measured it for PM100 and PM10, as you can see, but many concentrations were above the upper limit. It is a bit of a problem because the upper limit is lower than the TLV, so the occupational exposure limit. So we have to find a way to still define the concentration of these of these concentrations that are above the upper limits. There was some concern about nickel because there was nickel measured in some of the oxygen carriers, but here we see that the nickel concentration is very low because nickel is known for its health effects. Here we make the comparison with the occupational exposure limit. The orange cells were the red cells in the previous slide. So here I calculated the concentrations. How did I do it? We had the analysis of the original oxygen carriers. So we knew the ratios of the different elements. Because it are all metal oxides, we can assume that that the pattern in the oxygen carrier and in the dust will be about the same. It's not that there's some volatile substance in there. So, and with these ratios, I calculated then the concentrations in the dust. These concentrations are then compared with the TLV to establish the risk index. The TLV values are the values that are used in Belgium. Except for the aluminium, it's from OSHA, because there is no TLV value in Belgium. For the iron, there is only a PM4 occupational exposure limit, not for the PM100. I still used the PM4 to compare it with the PM100, so it's very, very conservative. But still, the risk index is below 1 for iron. When the risk index is below 1, there is an acceptable risk. When the risk index is above 1, there is a risk. The measures have to be taken. When the risk is between 0.1 and 1, there is some concern, so attention has to be paid. We see here that for there is only one element where in red. That is the manganese. It's 4 micrograms. It's 4. The risk index is 4, so while it should be 1 or less. For the other elements, there is no concern, except for the some are between 0.1 and 1. So the calcium, the aluminium, and the copper in the copper impregnated aluminum oxide. Then we also calculated the exposure with the Stoffen-Manager model, because the Stoffen-Manager model gives exposure scenarios that resemble the real life situation. Because what we did was just generate some dust, but here we can be more precise. So we have to first define a scenario. The scenario I used was material delivery on an industrial scale, so in a silo. The dustiness, yes, it are granules and grains. The handling, it's working with products with still relatively high speed with a certain degree of dispersion. The duration is up to 2 hours a day. It's once a month. The area is regularly cleaned and inspected and maintenance. The location is outside. There is local exhaust ventilation present, but there's no personal protection equipment worn. And so the model calculates that is nearly 0.8 milligrams per cubic meter for 8 hours activity and 0.2 milligrams per cubic meter for 2 hours activity. When we compare then so this is a total dust concentration. Then again, I use the ratios to calculate the concentrations from that measured total concentration. And here we see, when we calculate the risk index again, that the manganese risk index is 2.3, while it was 4 in the dust. So it is a little bit lower, but still too high. Of course, also the concern in realistic scenarios also stays there. So the concentrations are nearly half of the concentrations in the dust. Then what are the health effects of the different elements? So in the C28, the manganese, titanium, calcium oxide oxygen carrier, it's a very complex oxides, so we have to look for some surrogate substances. We chose some simple oxides. We see that there the manganese oxides, the oxides in the C28 have a very low concern. For the iron impregnated, there's a moderate concern for the iron oxide, for a moderate concern for human health, and there is no or low concern for the for the elements in the copper impregnated element oxide. So we measured the health effects in vitro tests, as I told. So it's according to the alternative 3R approaches for human health. So R stands for replace, reduce, and refine animal experiments. So replace animal experiments, for example, by in vitro. So in vitro is just cultures, cell cultures, for example, in glassware. Yes. You can reduce animal experiments, and you can also refine animal experiments by using less animals per experiment. So, but here we used the in vitro experiments. First, there was a developmental and embryotoxicity test. It is done with a zebrafish embryo test, so that is an in vitro test. Although it's done with an animal, the outcome is relevant for human health. So it says something about the developmental, the impact on the development and on the malformations of the embryo. So that's called teratogenicity. Other experiments, but they are not, they are planned, they are not done yet, are the inhalation toxicity. So we are using the dust and taking some cell lines, human cell lines, and expose these cell lines to the dust. And they will show or not show whether there is oxidative stress or whether the cells are viable, etc. And they will also indicate whether there is a concern for human health with the dust, so with the dust to which the workers are exposed. The test with the zebrafish, so that are relevant, of which the results are relevant for human toxicity, these tests are performed. It's so 24 hours, the oxygen carriers are stirred 24 hours in medium, and then the medium is used, so the particles that are sunk are not used. It's only the medium that is used for testing. The zebrafish are exposed in that water-soluble fraction, and here we see that for the embryotoxicity, so for death, there is no effects with none of the three oxygen carriers, because the last one, the copper impregnated, there were 2 batches tested For the developmental toxicity, we see no effect for the C28 and the iron impregnated oxygen carrier, but we see teratogenicity up to 67 and even 83%, even when we dilute the water-soluble fraction to 6.25%. So that is really maybe a concern, and that has to be investigated further. But there are no lethal effects. It's only malformations. So what are we going to do next? Next, we're going to do the in vitro tests for human inhalation. So with the dust exposing cells to the dust. We're going to make real-life process descriptions and operational conditions and develop exposure scenarios. We're going to measure in a pilot plant, so real-life measurements. We are going to calculate also exposure, these scenarios in exposure models, like we did for the Stoffen manager. Then at last we're going to do risk characterization and give risk recommendation where needed. These are the 16 partners that were involved, so it's from industry, technical university, research institutes, some large electricity producers. And if you have any questions, please do so.